All right. Welcome everyone. Um, Today we are going to look at the periodic table. You realize that the periodic table is very important in chemistry. It carries information that we want you to know, such that you can be able to read it and understand the terminologies, the words used there, the symbols used there. You need to understand them. You don't necessarily need to memorize the periodic table, no. Why? Because usually at the back of your examination, you will have the periodic table there for you to use. So you don't really need to memorize. You don't have to force it into your head that you can actually draw the periodic table, not necessarily. You just need to know how to read it. That's what you need, right? So let's go into this. Let's start with the basics. We know that we have a number of elements, about 118 elements that we know. So we all know matter, and we say that matter consists of atoms. Okay, these atoms actually are the ones that make up elements. Everything around us is actually made up of elements. Even the food that we eat has elements: carbon, hydrogen, oxygen, and others, nitrogen, and many other elements. Okay, so these elements are the ones that we usually see in chemical reactions. So, for example, you have hydrogen reacting with oxygen. Of course, these exist as molecules to form water, form a molecule, to form molecules of water, or basically to form water. These words should not basically confuse you. What we are basically saying is that element consists of atoms, which are basically the smallest unit of an element that can participate in a chemical reaction. Okay, we are saying that we have a lot of elements, and these elements, each of these elements consists of very many atoms, and the atoms are the ones that actually participate in chemical reactions. Okay, because we have very many elements, 118 elements, how do we differentiate between them? We differentiate between them using the number of protons. The number of protons in the nucleus of an atom is what differentiates each element from the other. Okay, so you cannot have more than two elements that have the same atomic number. That's not possible. Okay, so atomic number, the definition is that atomic number is the number of protons in the nucleus of an atom. Okay, so each element has a unique atomic number, and this determines its reactions or its properties. Okay, now we have those many elements, right? So how can we present them in an organized way? The periodic table answers that question. So the periodic table has all these elements, okay, organized according to their atomic numbers, according to the number of protons. Okay, so this is what you see here. This is what we call the periodic table. That is the periodic table. Usually, you will not see this in your periodic table. You will not see this part in most of the periodic tables that you interact with, because we are not concerned with that at the moment. So you definitely see this part. This is what you will always see. Okay, so that is what we call the periodic table. It has rows and columns. These are the columns. This is a column. This is a column. This is a column. And then this is a row. This is a row. This is a row. That is a row. This is a row. This is a row. That is a row. Right? So what did this actually represent? Okay. The columns represent groups, and then the rows represent periods. So we have period 1, period 2, period 3, period 4, okay, period 7. And then we have group 1, group 2, group 3, okay. That is, for now, that's what I want you to know, that this is the periodic table. We concentrate on this upper part. This lower part is not our concern at this level, right? So let's go into the details of the periodic table. In each let's call this each square, like that, you will see we will have one element. It represents an element, okay, and its symbol, which is a symbol, is a, we are going to say that a symbol is one or two letters that represent an element. One or two letters that represent an element. So for us in chemistry, when we are writing a chemical equation, if you're saying what a hydrogen reacts with the oxygen to form water, we can use the words, that is the word equation, or we can use what we call a chemical equation. So we use the chemical symbols to represent that. So we can say hydrogen, which is a gas, reacts with oxygen, which is also a gas, to give us water, okay, to give us water, which is a liquid. So this is a chemical equation. These are symbols, okay? Those are chemical symbols. They represent, this H represents hydrogen, this O represents oxygen, right? So this here, the first element here is hydrogen, and then oxygen is here. This is where you get your oxygen, okay? So all these ones here are all symbols for the different elements. We usually focus a lot on the first 20 elements of the periodic table. These ones fall under transition elements. We don't focus a lot on them. So the first 20 coming up to here, and then coming up to there. That's where we focus on. So the symbols for the first 20 elements are here. Hydrogen is capital H. That's a rule. If you write a small h, if you write this, no, that's wrong. That's not the right one. It has to be capital H, a clear capital H, not a small. This one's wrong, okay? And then we have elements that have two letters representing them, okay? So helium here is He. Usually the first letter has to be capital. The next that follows it has to be a lowercase or a small letter. So helium, you cannot write helium like this. No, that's wrong. It is H, capital H, and then a small e. That is helium. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Those are the first 20 elements of the periodic table that you should be familiar with. You should be familiar with the chemistry of this. Okay? So we go through the rules again. The first letter. If it is only one letter, it has to be capital. If there are two letters, the first is capital, the second is a small letter. These names can come from, the symbols can come from the name directly, or they can come, the names can are derived from, for example, Latin language. So that is something that perhaps you can know. They do not have numbers. The symbols don't have numbers, so we cannot write. If we ask you in the exam, write the symbol for oxygen, you cannot write like this. No, please, that's not right. The symbol of oxygen is the capital O, like that. The symbol of oxygen is capital O, like that. It is not having any figure. Okay, they do not have any figure, they do not have any special characters. Let us look at what we call the atom notation. What does this really mean? In chemistry, we have what we can call conventional way of writing things, conventional way of communicating information, so that any chemist around the world knows what we are communicating. Okay, so that applies to the chemical formula, that applies to the chemical equations, that applies to the symbol, the chemical symbols, but that also applies to atomic number, how we communicate the atomic number, and also how we communicate what we call the atomic mass. Okay, what we call the atomic mass. Now, when you find, for example, using the illustration that we have on the slide, W is standing in for the symbol of any element. So W can be any element. It can be sodium, it can be chlorine, it can be anything. It can be the symbol of any of those elements or other elements that I've not mentioned. So what does this really mean? For each element, we can communicate using its symbol, that we know that already, but also we can tell, we can communicate about its atomic number, which is A. A represents the atomic number. So if you find any figure replacing A, that figure is basically the atomic number, and it is the number of protons. Now, any number that is below that, the symbol of that element is the atomic mass. So what is the atomic mass? Now, for you to understand what atomic mass is, you need to understand that we have what we call isotopes. Isotopes, atoms of the same element. They have the same number of protons, but different number of neutrons, and therefore they have different atomic masses. Okay, and in this, they actually have different mass numbers, not masses. They have different mass numbers. Those are what we call the isotopes. Now, if we take the weight, the average weight, or what we call the weighted average of the different isotopes, we get what we call the atomic mass. Okay, so what is written down is always the atomic mass, and what is written up is the mass, is the atomic number, which is the number of protons. Okay, we already know that in the periodic table, as you move down the same group, as you move across the same period. So what is the same group, the same period? What do they mean? If the elements belong to the same group, it means that they have the same number of electrons in the outermost shell, if they belong to the same group. If they belong to the same period, they have the same number of energy levels. What are energy levels? So you have an atom, and in an atom you have the nucleus. In the nucleus you have the protons and the neutrons, and then the electrons are spread across the energy levels. So that is energy level 1, and then this is energy level 2, and this is energy level 3. So along these energy levels you have electrons. Okay, so if this is the nucleus, this element here has energy level 1, 2, 3. So it belongs to period 3. And we write period 3 as in terms of Roman numerals. It's the same way we write the periods. They're also written in Roman numerals. So the periodic table has broad categories. The first categorization that I want you to note is this one, where we have what we call the main group elements and then what we call the transition elements. Now, the yellow part, this one here, those are main group elements. Again, these ones also are main group elements. But what you find in the middle, these are the transition elements. And they have their unique characteristics that we shall look at later. So the periodic table, after arranging the elements according to their increasing atomic numbers, there are categories that come up. And for example, this categorization is because of the characteristics, the general characteristics of the elements within these categories, as we shall see later on. But one major thing that the periodic table also gives us is the categorization of these elements according to their nature. So what nature do we have here? We have metals, group 1 here, group 2, and then group 3 are basically metals. Okay, metals, the ones, the group 3 beside here are metals. And then you have those that are in between. Okay, basically these are the metals that we commonly refer to. Okay, but also these ones in the middle here, going like this. Okay, these are all metals here. Those are all what? Those are all metals. But in between the metals and the non-metals, we have what we call metalloids. These ones are metalloids. They are not metals and they are not really completely non-metals. Okay, they're just in between. We can call them semi-metals. Okay, they have properties that are in between the non-metals and metals. So here we have barium and silicon. Okay, those are metalloids. We are focusing on them because they belong to the first 20 elements. Remember, our focus is on the first 20 elements. So we are saying that the periodic table allows us to group categories elements into groups: the metals, and then the non-metals, and then the metalloids. But we also have another category here. These ones here. These ones are what we call the noble gases. Okay. So the non-metals, we have seen them, and then the noble gases, we have also seen them. Okay. We'll look at each of these, the chemistry of each of these groups of metals. And in between, remember what we said, that we have the main groups And then we have these ones in the middle. These ones, we call them the transition elements. And they are quite unique because they have variable characteristics. That is to say that their properties are actually varying a lot. So you cannot really predict their characteristics because one of the reasons is that they have variable oxidation states. Okay, they can lose or gain different number of electrons. So it's not very easy to really predict the nature of their reactions. So across the periodic table, there are some things that we can predict. Reactivity, especially in the metals. As you move down the group, the reactivity increases. Reactivity is basically the tendency to react with other elements. So reactivity increases as you go down the group. What is the reason? Is that as you move down the group, the atomic size of the atomic size of the element actually increases. And when it increases, it means that the force of attraction between the nuclear attraction or the nuclear charge attracting the electrons decreases, and therefore it is easy for the electrons to be lost, the outermost electrons to be lost, and therefore they can easily participate in a reaction. So the easy they can lose the electron, the outermost electrons, the better. And that means the easier the reaction will happen. But the harder it is, then it means that you will not have a reaction happening. But when we move to non-metals, for them, they are interested in gaining electrons. Metals are interested in losing electrons. Non-metals are interested in gaining electrons. So the stronger the force pulling, the better for them. Unfortunately, as you move down the group, the atomic size increases. That means the force of attraction also decreases. So that means that you cannot, the non-metals can, as you move down the group, cannot attract electrons. So they cannot easily gain electrons as you move down the group. And that's why the reactivity goes down. And then what happens if you move across the period in this way, like this? What happens? There is no uniform trend. Okay, there is a decrease from group 1 to group 4, and then there is an increase up to group 7, and then there is a sharp decrease with group 8. So group 8, they are these ones that we said they are basically inert gases, noble gases. They have what you call a stable configuration, and therefore they do not participate in a lot of chemical reactions. So that's why sometimes we call them inert gases. Okay, so what is the explanation? As we move across the period from left to right, the effective nuclear charge decreases, making the attraction between the nuclear charge or the nucleus and the outermost electrons are stronger. And this affects the ability to either gain or lose electrons. Okay, so that marks the end of this presentation, where we have looked at the periodic table. We said that the periodic table contains elements arranged according to their atomic numbers. The atomic number is what we call the number of protons in the nucleus of an atom. It gives, the atomic number gives the elements their unique properties. Okay, so each element has its own atomic number, and therefore we can say that the number of electrons in the outermost shell gives what we call the group. And if we categorize all these elements according to their groups, we will find out that there are patterns in terms of reaction. Okay. And then also when we categorize them according to the number of shells that they have, we are basically talking about the periods, and also still there is some pattern there. And overall, the interpretation of the reading of the periodic table depends on you understanding properly what we call the atomic notation, where you have the symbol, and then you have the atomic number up, and then you have the atomic mass down. Okay, and there are rules that you need to follow when writing chemical symbols. Chemical symbols are very important in writing chemical equations. Thank you.